Hello folks and welcome to this well test session. On this particular presentation we're going to have a look at how to create a well test file using Kappa Saphir. We just opened eCreen with Kappa Saphir and we're going to create a well test file. So we need 5 main inputs. The type of well, whether it's an oil producer, a gas producer or water injector. The PVT data, so formation volume factor, viscosity, fluid compressibility. The static data, so net reservoir thickness, initial water saturation, porosity, wellbore radius, the rate data, and the pressure data. So for this particular example, we're going to use a vertical well in an oil reservoir, and this is a production well. So we've got a permanent downhole gauge. So we've got other documents. We've got this Word document showing the fluid properties. So this is coming from production well, and the reservoir properties. So the porosity, the water saturation, the net reservoir thickness, the rock compressibility, the water compressibility, wellbore radius. We've got the surface measurement and the downhole gauge pressure in an Excel spreadsheet. It's this one. So this is showing the rate measurement. So the production well W1 came online on 1st of November 2013, and we managed to take 3 production flow tests. These are commonly called well test data, which is not exactly correct. These are production flow tests. So we flow the well through a test separator on the platform for a couple of hours and end up with an average oil rate and water rate for this particular date. We don't have the gas rate. There is some uncertainty on the gas rate due to some issue with the gas venturi meter on the test separator. But let's assume that the well is producing above bubble point. We don't have any free gas, and we're going to confirm this having a look at the derivative plots for the different PBUs. So in this particular case, we've got 3 production flow tests beginning of November when the well came online, flowing at about an average of 360 cubic meter per day for the oil rate, and an average of about 4.5 cubic meter per day for the water rate. So in this particular scenario, the water rate can be neglected compared to the oil rate. We've got only one dominant phase, is the oil phase. As well on this tab, we've got pressure data, and this is with few hour interval. So we asked the data processing software and we extracted pressure data with some few hours interval, just to give us the big picture. Since production startup, we can spot the different pressure buildup PBU test, and we can grab more details for this PBU, so we can acquire data with higher sampling. And this is the case here. PBU1, we've got some few seconds interval, as well as PBU2 here. As you can see, we've got a couple of seconds. So in Excel spreadsheet, you need to make sure that the seconds are visible. If they are not, if you only see 16:02 for all these points, Kappa Saphir will think that this is only one point, okay, at 4 p.m. 02. So try to make sure that the seconds are visible on your Excel spreadsheet. And it's the same with Pi software. Okay, so I think we've got all now to start. So let's go back to our blank file. So the first thing you need to do is to go on this icon here and create a new file. So now we see that this window is separated by 4 quadrants, 4 parts. We've got the type of test, the reference time, the fluid type, and whether we want standard analysis or something more fancy, nonlinear analysis for shale gas or coal-based methane, multi-layer commingle, formation test, slug test. In this particular case, this is production well. We've got standard analysis. We want to have a look at the production PBUs over time. Reference time, we've got 1st of November 2013. The well came online at that time. We've got an oil reservoir. Okay, otherwise we could have selected gas for gas well, a water injector. We've got also the option of the oil, a single phase pseudo pressure. This, I think, is for cases of reservoir with compaction issue, where density, compressibility, etc. can vary with pressure. In our particular case, we've got single-phase oil, and with pressure above the bubble point pressure, the PVT parameters can be assumed as constant as well. Even if you're producing a bit of water, as is our case here, okay, don't take the water here at this point, okay, only use the oil. You're gonna neglect the water rate. If you tick this box here, like this, now you are going into a multi-phase flow analysis. And pressure tangent analysis is going to give you some approximation with multi-phase flow analysis. In this particular case, as we selected two-phase, now Saphir is going to use the Perrine method, which is an approximation and assume that you can convert all these different phase rates into an equivalent single-phase liquid rate at the sand phase. Okay, this is approximation. In this particular case, we need to use the dominant oil phase and neglect the water rate. Type of test standard, we're not going to do any interference study. For the wellbore radius, we've got the standard 0.354. There we go. For the pay zone, we've got a net reservoir thickness of about 200 feet. So I'm going to input this one here. And for the porosity, you can see now it's not a number in percent, it's fractional number. We've got a porosity of 25% or 0.25. There we go. We can click on next, and now we need to input the PVT parameters. This is an oil production well, and we already got the fluid properties. So formation volume factor of 1.3, like this, a viscosity of 0.4. And you can input directly a total compressibility, or you can use the advanced mode here, input the different saturation for the different fluids with the associated compressibility, then the raw compressibility, and that's going to calculate the total compressibility as the sum of the raw compressibility plus the fluid saturation multiplied by the associated compressibility. So SF plus, in our case, we've got some water saturation, so SW multiplied by CW plus SO multiplied by CO. Okay. You can use some correlations for the PVT if you click on this, and you got different options, but we recommend to use the tidal. Okay. This option is probably for numerical well test when you got multi-phase flow in the reservoir. As we said before, multi-phase flow analysis is going to give you approximation, whether you are doing an analytical or a numerical well test analysis. Okay, so assume you've got a data, and if you've got a gas breakout, treat this as a fluid heterogeneity. You can select fluid type, the water as well. You can input an estimate of reservoir temperature, and you can use your pressure gauge for this. It measures the temperature as well. So during shut-in, you might have a good idea about the reservoir temperature. You can use an estimate of reservoir pressure, and you can input the pressure range minimum maximum. You can enter the water properties with the gravity or salinity and use the different correlations to obtain the water formation volume factor, the water compressibility, and water viscosity. The same for the oil. You can use you can input a specific gravity or an oil gradient in psi per foot or the IPI. And then you can use different correlations to get the formation volume factor, oil compressibility, and the oil viscosity. These correlations by default are good enough. And then you can have a look at the different parameters versus pressure. Okay, so let's have a look at the PVT now for a gas. What if we had a gas well? So let me change the reference phase. We've got gas. We don't go into multi-phase complex analysis. Click on next. Dry gas is selected, so that's fine. We can input pressure range. The reservoir temperature, a good estimate can be found in the pressure gauge during shut-in. An estimate of reservoir pressure. And so now we can input the water properties, but as well the gas properties. We've got two methods. We can directly input the specific gravity, okay, in this case 0.7, and the non-hydrocarbon elements. So let's say, and you need to make sure whether you need to input these as fractional number or as a percent. So in this case, we can say, for example, we've got 3%, 4% CO2, 0% for H2S, 0% for nitrogen. Otherwise, you can input directly the composition, the gas composition is going to calculate the PVT parameters. So click on this calculator to input the gas composition, and you can do it here with the non-hydrocarbon elements as well. And be careful, this is in percent. Okay. So either you input directly a specific gravity with the non-hydrocarbon elements, or you input the gas composition like this. You can use different correlations to calculate the Z factor, the viscosity, compressibility, formation volume factor. This is for the condensate. You can skip this as well. You don't want to enter into multi-phase flow analysis. It's going to give you some approximation. And these correlations are good enough as well by default. You can have a look at the different parameters versus pressure, etc. Okay, let's go back to, let's start again. Okay, I did a mistake, I went out. So I've got 0.354 for the base zone. I've got about 200 feet and a porosity of 0.25. 1st of November 2013, startup for the production well, standard. I've got an oil well. I'm going to neglect the water rate. I'm going to do a single phase oil analysis. This is where well test theory applies. Click on next. Formation volume factor, I've got 1.3, viscosity 0.4. I'm not going to use the correlations. I know these numbers, these are from nearby production wells. Total compressibility, I'm going to use the advanced mode. I've got an initial water saturation of, what is it, 35%. This is coming from the log as well. So let's use 0.35. Again, in Saphir, it's fractional number here. So a null saturation of 0.65. Water compressibility, we've got 0.3 E minus 5, 1 over psi. We've got 1 over psi here. So 0.3 E minus 5. For the oil compressibility, we've got 0.3 E minus 4, 1 over psi. So 0.3 E minus 4. And the rock compressibility, we've got 0.4 E minus 5. 0.4 E minus 5, 1 over psi. Now you can see the total compressibility has been automatically calculated. We can click on create. Right, so what we did now was to input the type of test. So it's an oil production well. We input the static data. So the net reservoir thickness, wellbore radius, porosity. We input the PVT data, so we input directly the formation volume factor, the viscosity, and the compressibility. We could have used the correlations, okay, based on an estimate of reservoir temperature, reservoir pressure, a specific gravity, and for gas you need to use a specific gravity with the non-hydrocarbon elements, or input directly a gas composition. So now the two other inputs that we need is to input the rate and the pressure data. So pressure data from the downhole gauge. You can do this at this page with these two icons. So you can load the rate and load the pressure like this. Or we can go back to our first tab, QA/QC, and load the pressure. Now you can see that Saphir is organized with these different tabs here and the different tabs here. So we've got the settings for your application settings, for your preference, for the units, for the number of decimals, etc. You've got our QA/QC data. You can load the pressure data. You can do a gauge comparison with this icon here. You can remove the tides with this icon. You can input the rate with load the rate. And as I click here, you see now automatically I switch to this tab. You got the interpretation here, so we can as well load the rate and load the pressure, as we said before. Automatically we switch to the tab called Analysis 1. We can extract the DP, so that's to select the different PBUs. And now you will have access to the well testing tools, the log-log plot, also called derivative plot, the superposition plot, and the production history plot, or also called data plot. You can investigate the convolution. You can select your interpretation model. You can improve your match with a nonlinear regression and do some sensitivities. You got more tools, in particular for well test design, and we've got a well test session on this. You can calculate the average reservoir pressure and the turbulence factor, plotting the skin versus the rate. You've got other fancy options like predict the rate based on the pressure, analysis of a mini frac. You've got the Kiwi option as well, which is, as it said here, artificial intelligence based advisor, model advisor. So based on the data, it's going to advise you some different models and try to do an automatic match. We don't recommend too much these options. It's better that you do it yourself. You will get a better understanding of your pressure tangent response. And then you've got the output tab for reporting. Okay, so let's go back to our QA/QC, and we went automatically to this QA/QC data tab, and we're going to load the pressure. And we've got an Excel spreadsheet. First thing we're going to do is to load the pressure with a few hour interval, just to give us some big picture. So I'm going to copy these two, like this, Control C, go back to Saphir, click on load. So I need to select first the type of data source. So I can select a file, so an ASCII file or text file. For example, I can select an Excel file. In this particular case, I just copy the two columns, so I can go on clipboard, and now I can see the date, the clock time, and the pressure. I can click on next. So now I need to specify in Saphir what is what. So I need to specify the column for the date, the clock time, and the pressure. By default, Saphir tried to identify what we've got here with decimal time and the pressure. You can see decimal time, the first number is 2, so that will be this column, and for the 10 for the pressure, so this is not correct. Usually this automatic process is quite good for when you've got a text file with decimal hours. But in this particular case, we need to specify the different columns. And we can do this with this line format here. So if we click on field, now we've got these 3 columns that has been automatically selected. We could have clicked on column and created our column ourselves, maintaining our left click on the mouse, like this. Then I can select the clock time, like this, and then the pressure, like this. So let's go back to our field. So I've got column A, this is the date, like this, and what we've got here is day, month, year. Okay, it's the 2nd of November 2013, so I'm going on the date, and now I've got different format, and this is the 31st of December, so this is the right format. I've got day, month, and year. Okay. My second column, column B, this is the clock time, so I'm going into time. I've got hour, minute, second, fraction. This is time auto. And column C, this is the pressure. There we go. And the pressure in PSI, so that's it. The time format, we've got points. We don't have durations. Reference time, I don't need to bother on this one because we've got date here. And I can load this. Delete all data. Apply to all. Okay, now I can see my gauge data, so the pressure data I copied, and this is the best picture. We can do that to then spot the different PBUs like this and require more details, require a higher sampling rate for these PBUs. You can see the pressure data here with the pressure pumps if you look at the right bottom corner. And now we can see that we've got some negative pressure data, so we need to remove these. And we can do that with the next step, edit data. You can select the pressure data with these different methods. So you can select all the display. You can select by data range, by time range. You can select individual points, or you can select with a box selection like this. And then I can click on this garbage icon to delete my selection. Okay, I want to delete, so I've selected 40 pressure points, and these are the rest which hasn't been selected. I want to delete these pressure points. I don't want to delete the non-selected pressure. So I click on OK, and that's it. And I can go back to my QA/QC. Now I can repeat the process and provide a bit more details on this PBU. So I'm going on Excel, select the first type, PBU1. I've got seconds here, so Saphir will think that these are different points. You need to show the seconds. Copy, go back to Saphir, load, clipboard, and now I can see the data that I copied with the seconds. Right, so now I want to tick this box. I want to append to existing data, and this is, I've got only one pressure gauge. This is my downhole permanent pressure gauge. Okay, why do I want to tick this? I just want to overwrite this PBU with this data with a bit more frequency. Okay, if I don't tick this option, now Saphir is going to believe this is another pressure gauge. So it's going to create another pressure gauge that you can see here on this drop down menu. I don't want to do that, so I'm going to click on next. Just want to make sure that the data has been correctly identified. So column A, I've got the date in day, months, year. Column B is my clock time, that's fine. And column C is my pressure, and that's PSI. It's okay, I've got points, I don't have durations, don't need to bother about the reference time. And I can click on load. So now I've got this warning, new time overlaps with previous data, stop load, or load all. I want to override all this, so I'm going to load all. And now you can see directly that you've got a bit more data. Click on zoom in, and you can see the different frequency. Zoom out or zoom reset like this. I'm going to do the same for the second PBU very quickly. So go to the PBU2 tab, copy, I've got seconds, so I'm happy. Go on load, clipboard, this is, I copy the data into the clipboard, so now I can see what I have. Append to existing data, I just want to overwrite this portion of the data on this existing gauge, or existing gauge here. Click on next, try to make sure that what I have is correctly identified. Yeah, date, clock time, pressure in PSI, that's fine. Load all, and now I can see I've got a bit more data for the PBU2. Okay, so I've just input the pressure data and I use an Excel spreadsheet. This is probably one of the methods that you might use for production wells if you've got a downhole pressure gauge. So you're gonna ask for data into a data processing software, you're gonna retrieve the data from there. And our recommendation is first retrieve the data with some few hours interval. You want to have a look at the big picture. You want to see the entire pressure trend, the entire pressure data history. And then you can spot the different pressure buildup or different shut-ins, and you can extract data with a higher sampling point. So in general, it should be a pressure point every 15 seconds or less. Okay, if you've got a gas high permeability reservoir, probably you want to go as low as 5 seconds or less. Okay, in the North Sea, for most of the reservoirs, which are mid to low perm, if you've got a pressure point every 30 seconds, that would be good enough. Another way to input the pressure data, in particular if you've got some exploration and appraisal well, or if you've got some memory gauges, that will be to deal with a text file. Okay, so I'm going to show you it's the same. If we want to load a text file, now we need to click on File and click on this icon. So Windows is going to open and you can select your file. So I'm going to select this pressure data. Okay, and now you can see the content, the first content of the pressure data, and I'm going to remove this tick here. I want to create another gauge data. So as if I've got a second pressure gauge. This is just to show you a simple example. Click on next. Right, so what I've got in this text file is decimal hour, okay, got a gauge reference and the pressure data and PSI. So For the line format, I'm going to click on 3. Decimal hours, Saphir picks quite well the different columns. So I've got my column A in decimal time and column B in pressure. Otherwise, I could have clicked on field. For column A, I've got decimal hours, decimal time like this. Column B, I will have my pressure data. Column A, decimal time. And column C is undefined, like this. Okay. Or column, this third option, if we've got some fixed column, and identify these two like this, maintaining the left click. Okay, let's go back to our 3. This is good enough. You spot quite well the 2 columns. Now I need to make sure that my reference time is correct and is equal to this one. So I've got the 1st of November 2013, which is 1st of November 2013 and midnight. So that's fine. Click on load, and now I can see my data from the text file in orange. So if I look here, I've got 2 gauges now. The pressure, which is just this text file, and the pressure data, which was from the Excel file. So I'm going to delete one of them. So just select active and click on the delete current gauge like this. Do you confirm destruction of pressure data? Yeah. So now I've got only 1 gauge data. Okay, with 2 PBEs. So the next step to do is to input the rate data. So I'm going to shift into this tab, edit rate. We make sure we remove the any outliers on the pressure data with edit data and this selecting with a box selection, and then removing the data with this icon, so we can shift on edit rate. And I'm going back to my Excel spreadsheet. I've got 3 production flow tests. Okay, so I'm going to only copy the date and the oil rate. As I said before, initially I'm going to neglect the water rate. Okay, when we compare these 2 rates. So I've got the date and these 3 production flow tests. We flow the one into a test separator for a couple of hours. This is in cubic meter per day. So copy this, go back to my Sapphire, load the rate. So I can load the rate from a file, or in this case, I copy from an Excel spreadsheet directly. So I'm going to select clipboard. I can see my date and the rate. Click on next. Right, so for the first column, this is not decimal time. So I'm going to select field. Column A, that's the date. I cannot see the date here, so I got a problem. And this is because my time format now is set to durations, which is the sort of default value for the rate. I need to select points. So now I go back to my first column, column A, and I've got my date, and this is day, month, year. So day, month, year is this one. Column B, this is the oil rate. So yeah, this has been selected correctly. And now I need to pay attention to the units. Okay, it's set to stock ton barrels per day. If I looked into my Excel file, I've got cubic meter per day. Okay, so I need to be careful here and select cubic meter per day. This is very simple, but it can be a source of error. Okay, so always try to pay attention to the units. Cubic meter per day. We've got date here, so we don't need to bother with the reference time. Now I can click on load. So I had 3 production flow tests. So now Saphir attempted to build a rate history based on this. Okay, so I can zoom out. And well, this is the true reality of a production well. I don't have any other data for the rate here. The well, unfortunately, hasn't been tested with a production flow test before the PBU. This is not best practice. We should try to do a production flow test before PBUs, especially before the first initial PBU, which is your reference PBU. And then you should try to flow test the well once per month. Okay. Then you will have a pretty good idea about your rate measurement and your rate data. And if you've got any opportunistic shut-in, like in this case here, you can reduce some uncertainty and you can use that to monitor your well and reservoir performance. Okay, so that's the most difficult job now. We need to estimate the rate data for this history here. And you can use different methods to do that. And at this point, this is a new production well, so we still don't have the allocation system for this well. based on your IPR and tubing performance, you can assume some rate. You can use productivity index as a method to calculate the rate. You can use choke model, etc. You can use simply the rates based on this pressure, the flowing pressure. You can see that now probably for this time period we've got more or less the same rate as this one. Now we've got the choke back. Maybe this period will be the same rate as this one, so probably this one. Rate of 0 for the PBU. Now we've got a gap of data. If you remember, the gauge were reading some negative values. We'll have to assume the start of the flow rate again around this point here. You can use, for example, the wing valve position to help you. Then you've got a flow period here, and probably more or less at the same rate as this one, and then a rate of 0. You can also QA/QC your rate data once you estimated the rate, comparing the different PBUs. To build the rate history, we've got different methods based on these different icons here. So the first one, called action, you can add a step at the beginning or at the end, or you can delete the first step. So I'm going to show you the first one, add a step at the beginning. So we're going to add a step here. So duration, let's say 50 hours, and for the rate, let's say 500 barrels per day. This is just an example. Click on OK, and now you see we add a first step at about 500 barrels per day, and that lasts 50 hours. You can also see this step on the first row in this table here. Okay, 50 hours, 500 barrels. So you can do the same and add a step at the end, so at this point here, or you can delete the first step. You've got another option, so let me zoom out a bit. Try to make sure that this is this option to move data to synchronize gauge. You want to make sure that start of the rate history coincide with your pressure data. So you can maintain your left click and move this change in rate up to this first point in the pressure data here. You can change the rate data on the table directly. So let's say now I've got a rate of 0 here, like this. So you can interact with this table as well, increasing, decreasing the duration, etc. For example, I can increase the duration like this for this rate, like this. Let me zoom out a bit. Here we go. Zoom out again. You could split a step as well. Here, for example, we've got the choke back. So choke back, let's say at 2000 barrels per day. Click on OK. You could move the data to the cursor like this. So bring this rate up to any point in time. Okay. So what we're going to do is we're going to split again the rate at this point and go back to where we were initially at 2273. Like this. I can mark, repeat this process to mark the shut-in. So after split a rate of 0, etc. I can add as well a step at the end. So let's say like this. Now about a duration of 200 hours maybe. So we've got about a duration of 200 hours, and let's assume a value of 2200 barrels per day. Here we go. It's missing a bit, and then a rate of 0, add a step at the end again, and a duration of say 100 hours, and the rate of 0 for the final shut-in. Okay, so the next thing we need to do now, so that was to show you the different method to build a rate history. The next thing we need to do now is to make sure that our rate data is in line with the pressure data. So every time we've got a shut-in, the rate shut-in should be in line with the first pressure point on your PBU. So let's start initially. So we need to make sure that this is in line roughly, and this is the best option to help us doing this. Very quick. Here we go. this, zooming out, zooming in again. So this is roughly in line. This is very important, so we need to zoom in again. So we need to make sure that this is in line with the first pressure point. Let me do this, maintaining the left click. I'm gonna zoom in again. Right, so up to this point, like this. Zoom out. And so now we are gonna assume, okay, we need to have a look at other methods to know where the rate starts again. We can use the position of the wing valve to help us. But we're gonna assume, let's say, the rate starts at this point. You can change it like this, or you can use this option and assume that, let's say, the well starts at this time. Okay? Let's say 960, for example, 960 hours. We can see that on the wing valve get open again. So I'm going to bring this up to the first point, do this in 2 steps, and then zoom in. If you don't do this, this will affect your derivative shape initially. So I can click here and, click. So I can click here and then doing this. Just to be precise again, let's zoom in and go. This is a bit of a tedious process, but it has to be done. And I think that's it. Right, so we input the pressure and we use the pressure as well to help us to input the rate history. Okay, so we've got 2 shut-ins. We need to make sure that the rate shut-in is in line with the first pressure point on our PBU, which we've just done. So now I think we are ready to have a look at the well testing tools. So we click on the Analysis 1 tab. Now we can see the historic plot showing, if I maximize this, showing our pressure and our rate versus time. It's mentioned liquid rate in barrels per day. But if we click here on document information, we can see that it's basically the oil rate, which has been selected. Click on cancel, minimize this. This icon is now available, the extract DP, so I can click on this one. And I can select the gauge. In this case, this is a production well. We've got a downhole pressure gauge. We've got only one gauge. But if we add an exploration appraisal well or memory gauges, we'll have different gauges to select. I can select the different PBUs I want to see, or I can, with this drop-down menu, or I can click on the list and select the different PBUs like this, etc. I prefer the display option, which is this one. If I click here, I can just do a left click on the different PBUs I want to see. And you can see now these 2 PBUs are highlighted in blue. Otherwise, I can just with a left click remove them or select both again. Click on OK. And now I see the different well testing tools. So I've got the log plot or derivative plot. So showing the delta P for the different PBU. The delta P, this is the pressure signal, and its derivative with respect to the superposition time. And this is plot versus the shut-in duration, delta T. Okay, this is log scale, as you can see. Then we've got the semi-log plot, or more commonly called the superposition plot, showing the pressure versus the superposition time. And in this particular case, this is the opposite of pi. We've got negative superposition time, and we need to look towards the right, okay, up to superposition time equal to 0, which means infinite shut-in duration. Okay. In general, we can remove the rate normalized for this superposition plot. And then we've got the history plot or the data plot showing the pressure and the rate versus time, and showing the 2 PBUs highlighted in blue, and we can see as well the code color. Okay, so for the first PBU, I've got the code color of orange. This is the one that we see here on the superposition plot, or we can see the log plot in orange here. And then I've got the second PBU with a shorter time duration highlighted in green,
and we can see the response on the derivative plot in green here, and that response lasts over a shorter time interval. In fact, if we can see, we've got about here, so this is a log scale, so this is 10 hours, now we've got 20, 30, 40, 50. So now we've got about 50 hours shut in for the second PBU. We've got quite some noise on the derivative plot. In fact, you can see we've got some cloud of data. And one way to minimize this noise is to go back, minimize the plot, go back to extract DP, click on OK. Now you've got this smoothing here. You can apply a very small smoothing of, let's say, 0.05. That's for the other PBU, 0.05. Here we go. And now you see the response has been smooth and you no longer see this cloud of data. Okay, right. A word of caution before going further. As we provide some smoothing coefficient, you need to be very careful with this one, because sometimes by default on some Kappa Saphir you'll see a smoothing coefficient of 0.1 or even more. Okay, you need to know that by over smoothing or by having a smoothing coefficient of 0.1 plus, sometimes you introduce some artificial features on your derivative. Okay, and now the danger is that you misinterpret or you mistakenly take these artificial features as flow regimes. Okay, that will be wrong. These are not representative of the well or the reservoir. Okay, so if you over smooth, you can introduce some artificial features on your derivative. Okay, so be careful with this one. Our recommendation is to always start with a smoothing coefficient of 0. Okay, always try to make sure that your smoothing coefficient of 0. You want to see the raw data. You don't want to apply any smoothing or anything on your data. Okay, and as well, if you've got a smoothing coefficient of 0, you will be able to see the noise. You will be able to spot some issues with your pressure gauge. For example, you will be able to spot some signs of wellbore phase overdistribution during shut-in. Okay, so I'm going to repeat that. So with a smoothing coefficient of 0, you will be able to spot some signs of wellbore phase overdistribution. During shut-in, you might have different phases in your tubing. Even if you've got single phase flow in your reservoir, you might have different phases in the tubing. And during shut-in, with expansion of the gas in the tubing, for example, or with natural gravity, these different phases are going to get well distributed, and the heavier fluid is going to fall down at the bottom of the well. So that means that the fluid density may change over time below the gauge. Okay, so the pressure at the gauge will no longer be a direct measurement of the pressure at the perforation. So the data won't be reliable for the analysis. It won't be representative of the well and the reservoir. It will only be affected by some dynamic behavior in the tubing, okay, some changes in fluid density. Really want to make sure that you know this before matching to this non-reliable data. And to do this, you need to make sure that the smoothing coefficient is equal to 0. We will have a well test session on this on the wellbore phase distribution. But you will find more information on the well test session called the common factors that complicate your well test analysis. As well, you want to make sure that your smoothing coefficient is equal to 0 because you want to spot any potential tidal effects. Okay, sometimes your pressure data at the gauge is going to be impacted by the tides. This is what we call the tidal effect. At late time, you might see some oscillations on your derivative, and which fit with some oscillations on your pressure data. Okay, smoothing is not the solution. You need to remove these tidal effects. And to do that, you need to go back to QA/QC and click on the tide icon. You need a reference tidal signal, and you can use some pressure gauges that you place at the seabed for offshore exploration of reservoir test, but you need to remove it this way. These tidal effects are going to mask your pressure tangent response. Okay, smoothing is not the solution. You might smooth and get a nice derivative response, it might not be representative, but you won't get rid of the pressure oscillations on your PBU, and then your deconvolution, you won't be able to recover reliable deconvol response. You won't be able to recover reliable deconvolution.
So always first use a smoothing of 0. Have a look at what's going on, and then if you're confident, you can use some smoothing, but use some low number, okay? Right, so on the derivative plot, quickly you can see that you've got an issue here at late time. So let's have a look at this PBU. This is the orange response. This is the PBU highlighted in orange. Let's have a look at the end of this PBU. This. Now you can see that you know that the gauge misread or stopped reading somehow here with some negative values. Now if you zoom in again, now you can see that the gauge reads a constant pressure value. So you need to remove this. So let's go back to our edit data. And what we're going to do is we're going to remove this. I'm going to select like this with the box selection, and I'm going to remove this data here. Okay, so now I can go back to my analysis one. I removed a bit of data reading constant pressure values. Now I can have a look at my derivative, and I see I don't see this issue anymore. Now I can see very consistent response, very consistent derivative plot showing a unit slope straight line and a hump indicative of some skin, maybe a stabilization around 10 to 20 hours, and then a late increase in the derivative, which could be due to the presence of the boundaries, maybe a fault. Now since the derivative plots are consistent, this gives us as well some confidence in our rate history. Okay, the rate history is more or less correct because these derivative plots are rate normalized. Okay, so they should share the same stabilization indicative of radial flow regime. This is dictated by the reservoir properties. Okay, so since they are rate normalized, normally here we should have PSI over barrels per day. Okay, but if you do right click, you can see now the rate normalized stick. So that means that our rate data are probably correct. If the rate data wasn't correct, then you will see a shift in the derivative in one of the derivative. Let's say, for example, if we go back to edit rates, and if we increase the rate here, let's say to 5,000 barrels per day, so now we've got some high rate. So what it's going to do is, as you increase the rate for before this PBU, the derivative plot for this PBU is going to be shift downwards. Okay, if we go on analysis 1 now, you see the green derivative data for this PBU is shift downwards. The two are no longer consistent, and you can see it's sort of like a parallel shift. Probably we know that the rate data before this PBU here is too high. Okay. You got more information on this on the well test session called the main factors that complicate the well test analysis. But this is quickly to show you. You can also use, just by looking at the plot, you can QA/QC your rate history, and you can do this to as well estimate your rate data. This assumes that you don't have any other changes in the well performance. Okay, you don't have any gas breakout or things like this. So let's go back to our edit rate and change directly on the table. We have 2200. Okay, and now again we got our consistent derivative. Right, so I think we're going to stop here. We created the well test file in Kappa Saphir. So we had 5 inputs. We specified the type of well and the type of test. So this was an oil producer. We input the static data, so porosity, net reservoir thickness, wellbore radius. We input the PVT data, the formation volume factor, the viscosity, the compressibility. We input the pressure data. We load the pressure from an Excel file or text file, and with this tab, edit data, we could remove some outliers on the pressure data. So we've got only one gauge. Okay, this is pressure data from the permanent downhole gauge. If we've got different gauges, if we run different memory gauges, or in an exploration or pressure context where we run multiple gauges along the tubing, we can do gauge comparison, and you can remove the tides with this icon.
More on this on the well test session called well test workflow and case study, okay, in the basic training course. We input the rate data here, so we load some rate from production flow test. If you've got individual meters, that's much easier for you. But then for an oil well, in general, you will have to test the well with test separator, and you'll have some few production flow tests on the rate history, so you will need to estimate the rate data if your allocation process is not up to date. So we've done that, and we show you the different icons. And then we had a look at the log-log plot or the derivative plot to QA/QC our work with the rate history, and to QA/QC the pressure and the rate data. Okay, so that's it, folks. Thanks very much for your attention, and see you then. Bye now.